We are talking about functions, right? Last time we talked about some examples of some wild functions. Today we are not going to talk about wild things. Actually, today is a big day. It's a shame some people aren't here to see it. We're going to talk about limits of functions. Limits. The real definition of a limit of a function. I'm talking about, something like lim x goes to 2 of f of x equals 5, right? What does that actually mean? We went to great lengths to talk about what it actually means to take the limit of a sequence, and it has some kind of epsilon thing. And there's going to be a similar type of definition for the limit of a function as a point approaches another. All right. I'm going to try and draw a picture of this. What it means is, x is approaching 2, and for the x values that are really close to 2, the y values will be really close to 5, is up here. So it means like there's sort of the graph, I guess looks something like that or something. I just made up the curve, but the important fact that I'm trying to talk about is that when the x values are near 2, around here, the y values end up being near 5, all right? We're going to try to write this this definition. If x values are near 2, then y values are near 5. All right. We're going to try to write this definition using some kind of epsilon business in order to express this near. The word near is really what you need the epsilon for. And we're not going to explicitly say something is near 5. We're really going to say absolute value f of x minus 5 is basically 0, or less than epsilon for any for all epsilon greater than 0, right? What's a little more complicated about this situation than the situation for sequences is we actually have two things which are near two different things. In the case of a sequence, it's like when the n is big enough, then the a sub n is near whatever, right? But here we actually have two different nears. So there's going to be an epsilon, and there's what happened? I lost my full screen. I don't know why that happened. There's going to be an epsilon, and there's actually kind of like two epsilons in play. There's the one which describes how close the y values are to 5, and then there's the other one which describes how close the x values are to 2. We're not going to use epsilon for both of them. One is called epsilon and the other is called delta. So on the picture, what I imagine is I'm going to use epsilon for where the y value is. So I'm going to say something like this y value is within epsilon of 5. And on the picture, we could indicate that by putting this little neighborhood around 5, where this top one would be like 5 plus epsilon, and this bottom one would be like 5 minus epsilon. And we're saying really that the y value is sort of inside this little window here. The y value is within epsilon of 5 in the y direction, which means that that point is sort of vertically situated inside that strip there. And when is it that the y's are in this little band? That will be true as long as the x's are in a little band around 2. And for that, we use the letter delta. So this, I think of another little neighborhood over here, where this is 2 plus, it's a lowercase delta, which looks like that. Kind of like a D, I guess. And then this one is 2 minus delta. And there's a similar kind of band like this. And the idea is whenever the x is inside this neighborhood in the x-axis, the y value will end up inside this neighborhood in the y-axis. That's what we mean in a more specific, in a more technical sense. When I say when x is close to 2, the y value will be close to 5. It means when the x value is inside this neighborhood and you plug it into the function, it goes up into y values which are inside of this neighborhood. All right. This is the picture you should have in mind. We just have to express the fact that really both of epsilon and delta are supposed to represent sort of infinitely small things. And the typical way that we do that is by saying for all epsilon greater than 0, this blah, 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 this is true. And that's how we're going to do it. Although the fact is that when you imagine that epsilon can be as small as you like, but if you're looking at this picture here, you will realize that if you were to actually make the epsilon shrink down to 0, if the epsilon gets really, really small, even like this window sort of collapses vertically a little bit, this delta in compensation will have to get even smaller in order to still fit inside the neighborhood up here when you do the x value. So really what we're going to say is for every epsilon, no matter how small the epsilon is, it is possible, it is possible to find some delta neighborhood around here so that when you plug everything into the function, it ends up within epsilon of the 5, all right? This is important stuff. I pity the fool who missed class today. No matter how small the epsilon is up here, you can always find some delta, super small, so that the neighborhood around this 2 maps up inside this little neighborhood around the 5, all right? That's what I'm going to say. No matter how small the epsilon, so the real, it means for all epsilon greater than 0, that's what I said, no matter how small the epsilon, you can find some delta, so I say there exists delta greater than 0, such that what exactly it is whenever the x is inside this neighborhood, the y ends up inside this neighborhood. So the way we're going to write that is if x x. Can you leave a little blank spot right here? I'm going to insert one little technicality right there, but I want to say if x minus 2 less than delta, then f of x minus 5 less than epsilon, all right? That's using 2 and 5 as specific example numbers. All right? This is the basic idea. Any thoughts about that before I tell you the little small technicality that goes after the word if? The small technicality is, as you all know, there are some examples in calculus where the line, like it has an actual limit, but that right at that point, there's like a hole in the function and the point is filled in somewhere else, right? This sometimes happens in weird calculus examples. In that case, the limit still exists. The limit still goes to this point 5, even though that individual point might be somewhere else. And so in the definition here, we have to make allowances for the fact that when x actually equals 2, it could be somewhere totally different. And so the technicality is this. I just inserted a 0 here. So this says when x, the distance from x to 2 is less than delta but not 0. That is when x is not actually equal to 2, but it's nearby. Then the values approach 5. All the values are near 5. All right? This is how we are going to write the definition of this limit right there. Let me just write it again in generality. This is all about 2s and 5s. Of course, we usually don't use those as our numbers. So it says lim x goes to, so I'm going to, just to say this generally, I'll use c for that value down there and a big L for the value of the limit. So this means for all epsilon greater than 0, there exists delta greater than 0 such that 0 less than x minus c less than delta implies f of x minus L less than epsilon. This is super important, and you should memorize that, I guess. Like, you're going to be doing this so many times that I think you will naturally remember this, but this is what the limit of a function means. This looks like a bunch of nonsense if you are not familiar with this way of speaking about things, but the kind of to decode this a little bit, this part means something like if x is close to c, then That's easy enough. This means f of x is close to L, right? This is the proper way to express these ideas about something is really close to this, then something else is really close to this. It's the epsilons and the deltas. If x is close to c, then f of x is close to L. All right, so the way you demonstrate that a limit equals something or other is by these epsilons and deltas. People refer to this as epsilon and delta proofs. I remember when I don't know if you've ever heard that phrase. When I was in college, when I was like a young math major, I remember people said to me more than once, like, man, that real analysis, you got to do those epsilon delta proofs. And I was like, wow, that sounds complicated. I'm like, yeah, it's terrible. It's not so terrible. They are really very similar to proving that a sequence converges with the big N and the epsilon. It's a similar thing, only the set of tricks that you have to use is slightly different. But as long as you can kind of keep with the basic structure of the proofs, I would say these are not super hard to deal with. All right. One thing to say, you can also phrase this in more topologically or in terms of neighborhoods, which is sometimes, usually if you want to prove that a particular limit equals something, you usually wouldn't do it this way, but sometimes when we're just talking about limits in general, it's often easier to think of it in terms of neighborhoods. What this says is when the distance from x to c is less than delta, another way of saying that is, well, let me write the quantifiers. For all epsilon greater than 0, there exists delta greater than 0 such that the one on the left means x is within distance delta of c. Another way of saying that is x is in the neighborhood of c, the delta neighborhood of c, right? That means the same thing. It means x is inside the neighborhood around c. Implies, can anyone write that one in terms of a neighborhood? Something is in the neighborhood around something with radius something. Maybe keeping the picture in mind would be helpful. Sorry, my picture's all the way up here. But you can see the x down here is in this little neighborhood with radius delta. What about, can you say what's the other thing say? Yeah.
L is in the neighborhood, the epsilon neighborhood of f of x.
This is close. That's almost what I was going to say. Here on the picture, 5 is playing the role of L, right? So it seems to me what I'm talking about here is a neighborhood around L. Yeah, f of x is in the neighborhood around L with radius epsilon, like that. Yeah, great. And again, I should say, because of the technicality here, this disallows x equals c, so really you have to say, well, technicality. If x is in that neighborhood but not equal to c, then this other thing is true. This little technicality is a pain and is almost never relevant, so this is not something that is a big deal. Just because the only times it matters is in those weird examples where the curve looks continuous but then it has a single point out of place, which are mostly, those examples come up on like just made up calculus problems. Those are not things that typically happen very often. All right, this is another equivalent version of the definition, which, like I said, sometimes will be useful. Although if I ask you to prove the limit of a certain function is something, this is the one you're going to use, 9 out of 10 times. All right. In my opinion, this is like one of the great achievements of human mathematics, I would say. Just coming up with this very complicated definition for what is on the surface something very simple. People in middle school talk about what a continuous function is. Basically, a continuous function means that like this is always true of all the values of the function. When it's such a easy thing to wrap your mind around on a surface level, but so difficult, so complicated to technically write a correct definition. And it took people a very long time to come up with this. This is the classic example of, the sort of backwards nature of the history of mathematics, where the details of this were worked out centuries after people had been using calculus to solve real-world problems for a long time. And they didn't figure out the basic definitions for hundreds of years. All right, anyway, let's try a bunch of examples. I know it's been a while, but I got some for you all to try today. Maybe you missed doing that. Let's do one together, and then I got one for you to try. Let's show that lim x goes to 4 of 2x equals. Anybody tell me the answer, first of all? Any calculus wizards out there? 8. Yes, you are truly a wizard of calculus. Yeah, this is something that's obvious to a calculus student, and for us it will take 10 minutes to demonstrate why it's actually true. The calculus student doesn't even think about why it's actually true. Let's do it. All right, so here you have to do like a little proof. These proofs, they always have a fairly standard structure. It looks like the proofs that we do for sequences. So you just sort of work it out, and usually if you know the proper little tricks, it should work out fine. You just have to know how to do it. So I'm going to begin by saying, let epsilon greater than 0 be given, just like for sequences. Now for sequences, I would say we will find n a natural number such that whatever, but this time we will find the delta. We'll find delta greater than 0. Delta is another real number, which has to be greater than 0, such that, and then I write, so this time it's this, 0 less than x minus, now you've got to put things in their right positions. What goes here? The 4, yeah, x is getting close to 4. So what you write here is the distance from x to 4, which is this absolute value. Less than delta implies, and then over here it's f of x minus L. F of x is 2x minus L is 8, less than epsilon. All right. This is the setup. Now, just like our proofs for sequences, we're going to do some sort of work on the side, which is not, technically speaking, part of the real proof, but it is going to inform, after this stuff, I'm going to say, let delta be something specific. It's always, something like epsilon over 2 or that kind of thing, just like we did for the sequences. But we have to work out what are we going to choose the delta to be. Inside here, just like with sequences, I'm going to try to simplify things as much as possible. Now, in the case of the sequences, you sort of are trying to solve for the n, if you recall doing this for sequences. In this case, we don't have an n. We have, instead of n over here, we have this thing. Really what you want to do over here is something like solve for absolute value x minus 4. This is weirder than solving for n, and so these proofs can sometimes require some stranger tricks, but that's what you want to do in this kind of a argument. Anybody see how to do that? In this case, it's not so hard. Yeah, factor out a 2 here. So I can pull 2 out of the absolute values. Is it legal to pull it all the way out of the absolute values? Yeah, it is, because it's positive. Then what remains is x minus 4. All right. So I solved for, I solved for x minus 4. Now I'll say something like, I want 2 times absolute value x minus 4 to be less than epsilon, right? Because I want absolute value 2 minus 8 to be less than epsilon. This is just like you do for sequences. So what I really want is x minus 4 to be less than epsilon over 2. And that's what the delta is going to be. See this x minus 4 less than delta. It looks just like this here. And so when I continue the proof, I say let delta be epsilon over 2. Oops. Writing in black now. All right. Let me just say, as a little bit of commentary here, just like for sequences, when simplifying in here, this one was very easy. All you had to do is factor 2. When simplifying, use equal or less than or equal. Remember, there were some examples where you we did some examples which involved fractions where you play some simple tricks with the less than or equals to simplify things. And the same is true for these kinds of proofs too. This will come up later on, maybe not today, but eventually we'll do some more complicated ones where you have to use less than or equals. Anyway, let's see if we can finish the proof. So I say let delta equal epsilon over 2, and then I finish by saying something like, then if x minus 4 less than delta, we have, and now I do what I call the prestige, right? You just write out, you begin with 2x minus 8, and then I'm going to use less than or equal signs and end up with epsilon at the end, hopefully. So what do I do with this? I do the same simplification. Pull the 2 out, 2 times x minus 4. And then x minus 4 is assumed to be less than delta, so I can say this is less than 2 delta if you like, but delta is epsilon over 2, so this is 2 times epsilon over 2, which is epsilon. And that's what I want. All right? So the format of the proof is really the same as the sequences thing. It's just the details are a little different and technically a little weirder in here sometimes because the thing you're solving for is somewhat strange. All right. What are your questions about this one? I got one for you all to try. Yeah.
I just have a quick question.
Yes.
So how you said when simplifying use equals or less than or equal
Right.
to.
Yeah.
With the ones with the sequences, we are allowed to use just like less than. Is that not the case with these?
Oh, you can.
Because I felt like with those like fraction rules,
Yeah.
it was mainly we do less than.
Less than or equal is fine.
Okay.
I mean, if you think about it, in some steps you're using equal, in some steps you're using less than. That means you must also be able to use less than or equal. You're using both interchangeably. Most of the time with those fractions, it is true, most of the time they were strict less thans. But I think not always. Like we did some, I know you don't have total recall of every example we've ever done, but there was something like this, where we said that was less than or equal to 1 over n, because even though it is actually possible that the sign n equals 1, and maybe not for an integer, that's not possible. Anyway, less than or equal, yeah. I would say it's true. Usually it is just a straight up less than, so maybe that make you feel better. It can be an equal or a less than or less than. Yeah. All right, I got one for you all to try. See what you think of. This one is very similar. Show lim x goes to 5 of 2x plus 3 equals 13. See what you think. And then we'll do some that are a little more fancy. As I walk around, it looks like everyone's doing great. I'll do mine slowly up here. No spoilers. All right, can we chat about it? It looks like, everything pretty much worked like the example from before. You have to plug everything in properly, and then the 3 minus 13 gives you minus 10, and you can factor the 2 out, and you get x minus 5. There's some kind of magic that happens in there, that you actually start with this thing, and you are able to factor x minus 5. I don't know if that feels magical to anybody. It's something satisfying about that to me. Although I feel on some level that we just got lucky. Like, what if that number wasn't a 13? Then what would you do if this, instead of 2x minus 10, if it ended up being 2x minus 11? I suppose that would happen if this number instead was 14, right? This is a bit of a trick question. The answer is, do you have any?
It's like a less than. That's the void.
This is a good idea, although
Would it change like the whole?
I know for a fact that it wouldn't work in this case. It's difficult because it's inside of an absolute value, and you have to be careful about. The answer to my question is, what would you do if this was 14 instead of 13? Really, the question is, how would you do it if that was 14 instead of 13? And the answer is, you wouldn't do it because that's not even true anymore. Like, you're trying to prove this as if this was like its own little theorem. And it's only gonna work if it's 13 here, because it would be false if you put a 14 here. So the magic is happening sort of because it's true. You have like some kind of cosmic guarantee that the magic is gonna happen because that's actually the value of the limit. So that's something, I don't know, it feels weird to me, but weirdly satisfying. All right, let's try another example. There are some weird things that can happen here. What I just described cannot happen, that you get some other inappropriate number there. But here's an example which is maybe vaguely like that. How about this? Lim x goes to 3 of x squared minus x is, we can say, just by plugging it in here, 6, I think. This would be 9 minus 3 is 6. All right, so let's try and prove that. So I have my usual preamble here. The pledge. Let epsilon greater than 0 be given, and then we'll find delta greater than 0 such that 0 less than x minus 3 less than delta implies f of x, which is x squared minus x minus 6 less than epsilon. All right. So let's do our simplifying. What can I do with x squared minus x minus 6? Any suggestions? Factor. Yeah, this is the old, I don't know if you have anything in mind. Who knows if it's going to do any good, but you might as well factor that, right? If you've been raised as a math major. your instinct should be to factor. Can you say what are the factors? -3 and +2, right? And I also separated the absolute values because you can do that, right? Things which are multiplied inside the absolute values can be separated. All right. Now we have a bit of a problem which requires a new kind of trick. So what we have here is this, which is basically like delta, right? That's the thing which we're trying to solve for. But what about the other thing? What to do with this? You might think somehow I need to transform that into another x minus 3, but actually that's not really possible to do. X plus 2, what are we going to do with that? This is a new trick which actually this doesn't come up when you're working with sequences, so this is a new kind of thing that we have to talk about. What we're going to do is we imagine that, remember this represents the distance from x to 3, and we imagine that that distance is quite small. X is very close to 3. This represents the distance from x to 2. Over here, you mean? This is a good idea. Yeah, the fact is x is, you think in the back of your mind at least, x is basically 3. Now, that means that this is basically 0, but you can't replace this with 0 because then you will have nothing else to work with. But this part is not close to 0 at all, right? If x is close to 3, then this is kind of like 5. And so it should seem reasonable. We could more or less replace this with 5, right? Because x is basically like 5. Now, it's not exactly 5, and so we're not exactly going to replace this by 5, but here's the trick that we're going to do. Let's just assume the picture I have in mind is, here is 3, right? And x is near 3, somewhere in the neighborhood of 3. Then what is x plus 2? Is something near 5. Now, exactly how near to 5 is it? Well, I can say something like this. There are many ways you could decide to work this out, but I'm just going to say, let's assume that delta is less than 1. Like, I'm imagining delta is very, very small, but whatever. Let's just say it's going to be less than 1. What that means is x is actually in between, in fact, 2 and 4, right? If I'm assuming delta is less than 1, then x is between 2 and 4. And so, keeping it red here, then x, in particular, I'm going to say x is less than 4, because all I really care about is the less than sign, because that's what I'm going to use in my simplifying, is the less than. Then x is less than 4, and so x plus 2 is less than 6. And that's where I'm going to go from here. So this thing, sorry to draw big lines, this stuff here, I'm going to continue and say this is less than x minus 3 times 6. All right. You can't exactly put 5 there because x might be a little bit bigger than 3, which means x plus 2 might be a little bit bigger than 5. But if the delta is less than 1, which of course we expect the delta to be far less than 1, this is definitely true. The x plus 2 part there is less than 6. All right, and now from here we can continue the rest of the proof. So now I would say, just like before, I want this x minus 3 times 6 to be less than epsilon, and so I divide by 6. I make x minus 3 less than epsilon over 6, and that's what I'm going to choose to be my delta. All right, so this little trick involves, it's what you have to do when you factor something and you end up with like extra factors which don't look like the thing you're looking for. Instead of looking like delta, this actually looks like, it's just like some other number, and you have to figure out what that other number is. All right. let's see if we can continue the proof. So there's a little technicality. I'm not actually going to say let delta equal epsilon over 6 because this whole thing, this epsilon over 6, only works if the delta is originally less than 1. All right? So really what we have to say is we have to choose delta, first of all, so that it's less than 1, and also less than epsilon over 6. Now, you could just write those words, let delta be less than 1 and also less than epsilon over 6, but the cute sort of fancier way to do that is I say let delta equal the min of 1 and epsilon over 6. This is the same as saying let delta be less than 1 and also less than epsilon over 6, right? It's smaller than whatever is smaller, the 1 or the epsilon over 6. That's what this means. Yeah.
The one's smaller than the other. Or does it still work?
Yeah. I should say this just to be safe. Then you don't have to worry about that. I agree. That's a good thing to worry about. So I'm just saying delta is some number that's smaller than 1 and it's also smaller than epsilon over 6, which is what is required in order to make this little argument here work properly. All right? And then, now we can just write the rest of the proof. Okay, so then let x minus 3 less than delta, and then we have beginning with x squared minus x minus 6, I think, yeah. This again I will factor, x minus 3, x plus 2. But now I can say this is less than or equal to, x minus 3 is less than delta, which is less than epsilon over 6. And then the other part is less than or equal to 6 because of arguments that we said before. Actually, this could be a strict less than. It doesn't have to be less than or equal, but it doesn't really matter. No, actually, I think it does matter. Less than. Because I want to say eventually is less than epsilon, right? The x minus 3 part is smaller than delta. And for that I use epsilon over 6. And then the x plus 2 has to be less than 6 because of arguments that we said in red there. All right. This is a little tricky, I think, that this business about the 6 up there is takes a little bit of getting used to. Any questions about that one though? I got another one just to make sure we are okay with this, and that'll probably do it for today. All right, let's try one more that looks a little different. Let's do lim x goes to 1 of 5 plus x over x. We got fractions. Plugging in 1 here, the answer is 6, right? Let's see if we can do this. I start as usual. All right, it says 0 less than x minus 1 less than delta implies, and over here, f of x is this thing, 5 plus x over x minus 6. Less than epsilon. All right. No thoughts necessary yet. As usual, we are going to begin by trying to simplify that complicated thing over there. Absolute value, 5 plus x over x minus 6. Any suggestions? How can we simplify here? Yeah, make a common denominator. That's what you got to do if you're adding fractions or subtracting like this. So the denominator can be x, right? And it can be 5 plus x over x minus 6x over x. Combine the terms. It's 5 plus x will be 5 minus 5x, right? Divided by x. All right. Can we do anything with that? I'm trying to make it as best I can look like this. X minus 1 is what I'm looking for. Absolute value x minus 1. Any ideas? I see one somewhat obvious thing to do and another less obvious. Factor out the 5. Yeah, that's I would I would definitely do that, even if I don't know what good it does. 1 minus x up top over x. Is there any way to get x minus 1 out of that? How about here's something else. Because it's a fraction, I can just do absolute value on top and absolute value on the bottom. That is legal and recommended. All right, anyone see how to get x minus 1 out of that? Absolute value x minus 1? This is approaching sort of trick question territory. Would you believe me if I said absolute value 1 minus x equals absolute value x minus 1? They're the same because one is the negative of the other, right? This, if I were to multiply this by minus 1, it is that, right? So they're opposites, like the numbers. So that's actually the same. So this is really, I'm going to write it in a somewhat nicer way. This, right? Absolute value x minus 1 is the same as absolute value 1 minus x. I need absolute values around the x there, sorry. So when I look at this, how do I feel? I feel fine about the 5. You know, we're just going to like divide the 5 at the end anyway, epsilon over 5, whatever. This I feel okay about because this is what I wanted. This will turn into something like delta. This, though, is a problem that we need to think about. But this is the same kind of a thing from the example before. X is getting close to 1. And so, x is getting close to 1. So this 1 over x is really going to be something like 1 over 1. Now, it's not exactly like that. We have to say, again, a similar trick. I'm going to say, assume that delta is less than 1, then this part is going to be less than something else. Although, exactly that is not going to work because, unfortunately, this being in a denominator, if I actually use 1 for the delta, then that means that, remember the picture that you should have in mind is, here's 1, and x is in some neighborhood around that, right? Now, if that neighborhood is actually I don't want this neighborhood to stretch all the way to 0, because then this will get messed up, right? I'll get a 1 over 0, which is no good. So in this particular case, you have to say something like, let delta be, let's say less than a half. This is just to keep this little neighborhood small enough so that it doesn't include or touch 0. Because if I allow this neighborhood to touch 0, then when I try to plug in for 1 over x, I might get 1 over 0, which I don't want, all right? So I'm going to assume that delta is less than a half. Usually it doesn't really matter what you choose the delta to be, but here, just because I know I'm going to be dividing, I have to make sure this excludes 0, all right? Then, I will say actually, well, yeah, let me say it this way. I want to say x is, I'm going to use a greater than actually this time because I am going to end up dividing by this, whatever it is. Since it's in the denominator here, I want to find the biggest possible, I want the smallest possible value that the x could be. Can we fill in the blanks here? If delta is less than a half, that means this little region here is less than a half. You can say x is greater than, that means like 0 is over here. Really, it's between these two values, right? Yeah, I would say 1/2. It's between, if the delta is 1/2, then the x has to be between, this is 1/2 and this is 3/2. X is greater than 1/2. And that's what I'm going to plug in over here. Why I use greater than, usually I like to use less than. It's because this is in a denominator. So when I plug 1/2 in a denominator, it makes this whole thing less. It's because it's downstairs that I have to use the other one. If I was using less thans, I would have used 3/2. But because it's in a denominator, I use the other one. This is all takes a bit of getting used to, I know. All right, and then anyway, then this part here turns into I can say this is less than or equal to 5 absolute value x minus 1 times 1 over a half. That's 2. And combining that with the 5 gives me 10 times absolute value x minus 1. And so our usual steps give you x minus 1 is less than epsilon over 10. All right. This is the hard part. In our remaining 3 minutes, let's just finish writing the proof. So I'm going to say, let delta be less than, what do you have to say here? It's not just epsilon over 10. Yeah, it's the min, because remember, this epsilon over 10 is only working when delta is less than a half. So what do you say? Right. The min of 1/2 and epsilon over 10. Delta has to be less than a half and also less than epsilon over 10. Then if, now I'll just say the usual stuff. X minus 1 less than delta, we have absolute value. It was 5 plus x over x minus 6. This ended up being the same as 5 absolute value x minus 1 times 1 over absolute value x. And then this was less than or equal to 10 absolute value x minus 1 by the same reasons that we said above. And this is less than 10 times epsilon over 10. That's it. All right, I think that'll do it for today. This is how you show limits of functions. We'll have some more examples next time, and there'll be some on the homework for you to try out. Have a great weekend.